Formulas within each set identical enantiomers or diastereomers. The official definition for enantiomers is that they're non-superimposable mirror images, but in order for us to do this easier, I made my own definitions. So for enantiomers, all chiral centers in one molecule will be opposite of all the chiral centers in another molecule. So for example, if my molecule has a chiral center with configuration R, and then there is another molecule that's the same, but it has a chiral center with configuration S, they will be enantiomers. Diastereomers had at least one chiral center that is opposite and at least one that is the same. So they should have two or more chiral centers, and one of them will be opposite and one of them will be the same. For identical molecules, all chiral centers will have to have the same stereochemistry. So if my molecule is R and then R, and then my other molecule should be R and R as well. So all chiral centers will have the same stereochemistry for identical molecules. And I will also tell you how to identify a chiral center. So let's get started. In A, we see these two molecules, and a chiral center or chiral carbon is a carbon that is connected to 4 different groups. So here we see that this carbon is connected to OH, a hydrogen, carbon on this side, and carbon with chlorine on this side. All of these groups are different, so this is a chiral center, and I'm going to star it. And the carbon next to it is also connected to 4 different groups: chlorine, hydrogen, carbon on this side, carbon with OH on this side. Everything is different, so this is a chiral center as well. And if we look at both of these, it's the same. This is a chiral center and this is a chiral center, actually for all of them. Next, usually we can identify the R and S and see if they're the same or opposite, and that's how we will compare our molecules. In this case, however, there is an easier way to do it. I will show you both. So an easier way is to realize that if you put a line like this representing a mirror, it literally looks like these two are mirror images of one another. So if we drew a mirror image of this molecule, we would get this molecule exactly. H going this way, chlorine dash going this way, OH wedge going this way, hydrogen dash going this way. So if two molecules have chiral centers and they are mirror images of one another, they are enantiomers. This is enantiomers. But just to check it, we will also do the Rns configuration. So let's start. Let's start with this chiral center. In order for us to do an Rns configuration, we have to give priorities 1 through 4, where 4 is the smallest atomic number and 1 is the largest atomic number. So let's do it. We have hydrogen, chlorine connected to this carbon. We also have a carbon here and a carbon here. So this carbon, this chiral center, this chiral carbon is connected to a hydrogen, chlorine, carbon, and carbon. If you look at the periodic table, hydrogen is the smallest, it's 4, chlorine is the biggest one, and then between these two, who is winning? This carbon is connected to OH, and this carbon is not, it's only connected to hydrogen. So this is going to win 2, and this is going to win, and this must be 3. So we have 1, 2, 3. Now, if we connect 1, 2, 3, if it's going to the right, this is R, and if it's going this way, this is S. Also, we have to note that the smallest group has to be dashed. So group number 4 has to be dashed. If it's not dashed, we have to say the opposite stereochemistry. So I have put all of my numbers together. I have 1, 2, 3, 4, and it looks like we're going in this direction, which would be S. But because my number 4 is not dashed, I have to switch it, and this is going to be R. So this configuration must be R. Let's go to this carbon. Hydrogen is number 4. I have oxygen, carbon, carbon. And let me just erase to make to make things easier. So I'm going to say that this is R. Okay, oxygen, carbon, carbon. Who is bigger on the periodic table? You can see oxygen is bigger, so that's number 1. And between these two, who is bigger? This carbon is connected to chlorine and another carbon, and this one is not. So this must be 2, and this must be 3. Is my lowest group, group number 4, dashed? Yes, it is. That means I don't have to think any further. I can just connect the numbers 1 through 3. It's going this way, so this is S. Now let's look at this one. Hydrogen 4, chlorine 1. This carbon is going to win because it's connected to the OH, so this is 2 and this is 3. Again, my hydrogen is not on a dash, so I will have to change my stereochemistry. 1, 2, 3. It looks like it's going to the right, so it would be R, but because hydrogen is not on a dash, I have to switch it, so it's going to be S. So you can see that these two are opposite. Let's look at this. Chiral center, and let me erase it to make it easier. This carbon is connected to hydrogen, oxygen, carbon, and carbon. Hydrogen is the smallest, oxygen is the largest on the periodic table. This carbon is connected to a chlorine, and this carbon is not. It's only connected to hydrogen, so this wins 2, and this is 3. My hydrogen is dashed, it's going in, so I don't need to switch my stereochemistry. 1, 2, 3. It's going to the right, this way, clockwise, so it must be R. Now, let's compare my chiral centers. The chiral center here has opposite stereochemistry. This one is R, this one is S. The chiral center here also has opposite stereochemistry. This one is S, but this one is R. That is why my molecules are enantiomers. So, because I checked every chiral center and all chiral centers in the two molecules have opposite stereochemistry, these two molecules are enantiomers. And another way I did that is by seeing that they literally look like mirror images of one another, which was a quicker and faster way in this case. Let's go ahead and look at part B. Again, what I can do is I can identify my chiral centers whether they are R or S, and that will allow me to figure out if my molecules are enantiomers, diastereomers, or identical molecules. This one, hydrogen is 4, chlorine is 1, this carbon is connected to OH, this carbon is connected to hydrogens 2, and this must be 3. Now, 1 to 3, it looks like R, but because the hydrogen is not on a dash, I have to switch it, so this must be S. Let's look at this one, and let me erase to make it easier. You could actually just look at what I did here to see that this, well, actually it's just easier to do it again, so let's go ahead and do it. So, this chiral carbon is connected to hydrogen, oxygen, carbon, and carbon. Hydrogen is 4 because it's the smallest, oxygen is 1. This carbon is connected to chlorine, this one is just connected to hydrogens, which are not shown. So this is 2, and this is 3. 1, 2, 3, it looks like R. But again, because my lowest group, my group number 4 is not dashed, I'm going to switch the stereochemistry and say that this is S. So I have S and S configuration. Let's look here. Hydrogen 4, chlorine 1. This carbon is connected to OH. This carbon is connected to hydrogens. So this is 2, and this is 3. My lowest group is dashed, so we're good to go. 1, 2, 3. It looks like I'm going in this direction, counterclockwise. So this must be S. 1, 2, 3. Okay, now let's look at this one. 4, 1. This would be 2 as well because this carbon is connected to chlorine. This carbon is connected to all hydrogens. So this would be 3. 1, 2, 3. It looks like it's going in this direction, but because my lowest group is not on a dash, I have to switch it. So even though it looks like it's S, I'm going to switch it, so this must be R. Now, let's look at my chiral centers. I have S and S and S and R. So this chiral center, so what we can see is that at least one chiral center is opposite and at least one is the same. One of them, here I have S and S, and here I have S and R. So one of them stayed the same and another one switched. And that means that these are diastereomers. Just going to abbreviate it, diastereomers. Let's look at part C. This is 4, 1, this is 2, and 3. They all have the same substituents, so it gets easier numbering them. So 1 to 3, it looks like it's going to the right. However, my hydrogen is not on a dash, so I have to switch it. So this must be S. Actually, it's the same as here. Actually, the molecule here is the same as this one, right? So maybe I can just, instead of doing it again, I can just double check that it's the same. It is not. Now I see that this OH is dashed and here it is not. So let me do it. So this is S. And now let's do the second chiral center. This hydrogen is 4, oxygen is 1, carbon, carbon. This carbon is only hydrogens, and this carbon is connected to chlorine. So 2 and 3. Now I have 1, 2, 3. My lowest group, my group number 4 is dashed, so I don't need to switch the stereochemistry. And I go 1, 2, 3, and it looks like this must be R. Now let's go here. This hydrogen is 4, this chlorine is 1, this is 2, and this is 3. My lowest group is not dashed, so I will have to switch stereochemistry. 1, 2, 3 looks like it's going in this direction, which would be S. It's going counterclockwise, which would be S, but I have to switch it, so this must be R. This is 4, this is 1, this is 2. It already says 2 here, and this is 3. My lowest group again, my group number 4 is not dashed, so I will have to switch it again. It looks like it's going in the S direction, like this, but I have to switch it, so this must be R. So again, what are these molecules? Well, the chiral center that has a chlorine on, it has switched. The chiral center that has the OH on, it stayed the same. So if one chiral center switches and one stays the same, what do we have? We must have diastereomers, and I'm going to abbreviate it again. So let's just summarize what we have learned so far. In part A, when we identify our chiral centers, we saw that the carbon with the OH, it used to be S here, but it became R here. So the chiral center stereochemistry switched. And the chiral center with the chlorine was R here, but it became S. So both chiral centers have switched. That's why in A we have enantiomers. And another way we said we saw that is because there were mirror images of one another. In B, we see that the chiral center that has chlorine is S, and here it's still S, so this one stayed the same. But the chiral center with OH is S here, but it's R here, so this one switched. We went from SS to SR. If one stays the same and another switches, it's diastereomers. And we had the same situation in part C. We had SR on this left molecule, and then RR on the right molecule. This is Maya Alochi from Transformation Tutoring, and I really hope that you enjoyed my video, and I look forward to seeing you in more of my videos.